So the title of this chapter is Gradient, Divergence, and Curl, and that's because we are going to spend all of the chapter talking about the meaning and properties of these three operations. But to start off, I like ripping off the band-aid and showing you in a short video how to calculate the three things very quickly, so that you see that it's not that bad after all. It's actually a very simple concept to calculate. Okay, so let's do it. And to do that, we are going to ask Nabla for help. Okay, so the gradient. The gradient is an operation which acts on a scalar field So you apply the gradient, grad, to a scalar field, and the result is a vector field. And what is this gradient of operation? It's very easy. So let's say this vector field is f, and the input scalar field is phi. Okay. So the output of the gradient is this vector field f, which we say is equal to the gradient of phi. So this is like applying the function to phi. And the way you calculate it is simply you apply nabla to phi. Okay. What does this mean? Well, if we substitute the meaning of nabla, which is partial with respect to x, partial with respect to y, and partial with respect to z, we apply this to phi. So this means that phi is kind of multiplying each of the components, but it's not a multiplication because this is not a number, this is an operation. So when I say multiply, I mean do this operation on whatever you are multiplying it with, okay? So you end up with a vector which is the partial derivative of phi with respect to x, the partial derivative of phi with respect to y, and the partial derivative of phi with respect to z. And this is a vector, okay? So this is our vector f. So let's see an example. Calculate the gradient of the scalar field f of x, y, z equals x minus x times y plus z squared. So let's calculate the gradient. So our result, f, capital F, is equal to the gradient of f, which is equal to nabla applied to f, which is equal to the derivative of f with respect to x, the derivative of f with respect to y, and the derivative of f with respect to z, all written as a vector. So we can do the partial derivatives. So what is the partial derivative of f with respect to x? It's going to be 1 minus y. What is the partial derivative of f with respect to y? It's going to be 0 minus x plus 0. And what is the partial derivative of f with respect to z? It's going to be 0 plus 0 plus 2z. And this is it. This is your vector f, which depends on x, y, and z. And this is called the gradient. Next. Who's next? The divergence is next. So the divergence is an operation that acts on a vector field. Let's call it capital F vector. You apply the divergence, which we write as div, and the result is a scalar field. Let's call it lowercase f. Okay? And how do you calculate this scalar field, which is the divergence of f? That's very easy. The divergence of f, capital F, is equal to nabla dot product with f. Okay? So let's develop this. What does it mean? If you write nabla as the vector partial with respect to x, partial with respect to y, partial with respect to z, and then you do the dot product with vector field f, which has three components, f of x, f of y, and f of z. The result of this dot product, you know how to do a dot product, is this times this, plus this times this, plus this times this, which means you are doing the partial derivative of f of x with respect to x, plus the partial derivative of f of y with respect to y, plus the partial derivative of f of z with respect to z. And this is a scalar, right? Because the dot product always results in a scalar. And this scalar is your vector field small f of x, y, z. Okay? So let's do an example. Calculate the divergence of the vector field f as a function of x, y, z, and you can see that this is a vector, right? Because you have three components: the x component, the y component, and the z component, which we could label as fx. This would be fy, and this would be f of z. So now we are going to calculate the divergence of f. So we start here. Divergence of f is equal to nabla dot f, which is equal to the partial of f of x with respect to x, plus the partial of f of y with respect to y, plus the partial of f of z with respect to z. So now we have to calculate those partial derivatives. So what's the partial of f of x with respect to x? F of x is 3y. What is the partial of 3y with respect to x? It's 0. Plus the partial of f of y with respect to y. So what is the partial derivative of 6y minus x e to the y with respect to y? So it's going to be 6 minus x e to the y, right? Because we are treating x as if it was a constant, and it's multiplying an exponential of y, whose derivative is the exponential of y. And then plus this third term here, which is the partial derivative of f of z with respect to z. Okay, so we need to do the derivative of xz. So the derivative with respect to z of x times z to the power 1/2. So this is going to be equal to 1/2 times the derivative of the parenthesis with respect to z, which is x, times x times z to the power of 1/2 minus 1, right? So this is going to be so x will be to the power of 1 times x to the power minus 1/2, so that will be x to the half. So we will have 1/2 x to the 1/2 z to the minus 1/2. Okay, and this is it. This is the divergence of the vector field f. Okay, who's next? We are only left with the curl. So the curl is an operation which acts on a vector field, which we are going to call f. You apply the curl, and the result is another vector field, which let's call it c for curl. Okay, and how do we calculate it? Well, it's very easy. C is equal to the curl of f, and it is nabla vector cross product with f vector. Okay, see how nice it is. So the gradient was simply apply nabla to a scalar field phi. The divergence is simply do the dot product of nabla with the field f. And the curl is simply do the cross product of nabla with the field f. Okay, so let's do that. What does it mean? It means we have this vector nabla, which has derivative with respect to x, with respect to y, and with respect to z as the three components. Cross product vector field f, which has f of x, f of y, and f of z as the three components. So now we need to do the cross product, which, as you know, you have to write this, then the first vector, which is the nabla operator, and then the vector field fx, fy, fz, and now you need to expand this this determinant. So the result is x hat times the determinant of this, and remember, whenever we multiply an operator with a component of the field, it means apply that operation to that component. So that will be the partial derivative of fz with respect to y minus the partial derivative of fy with respect to z. Then minus y hat, but let me put plus y hat and flip the sign of what's inside, okay? So I need to calculate the minus determinant of this, which will be this times this minus this times this. So it will be the partial of f of x with respect to z minus the partial of f of z with respect to x, and then plus z hat times the determinant that results from this, which is going to be this times this minus this times this. So it's going to be partial of f of y with respect to x minus partial of f of x with respect to y. Okay, and this is a vector which depends on x, y, z, so this is called our vector c, which is a function of x, y, z. Okay, let's do an example of this. calculate the curl of the vector field f of x, y, z equals this thing. So this thing has three components. This time I didn't write it as a column vector. I wrote it using the expansion with the basis vectors, right? But you can tell that this is fx, this is fy, and this is fz. So we need to apply all of those partial derivatives. So C, vector field, is the curl of f, which is equal to, and now maybe I can copy. Let me copy this big expression. As you can see, the curl is the longest to calculate simply because it involves lots of operations. Let me make it smaller. Yeah. So now I need to calculate all of these partial derivatives of each component with respect to each of the others. Okay. So the result is going to be x hat times, what's the partial of fz with respect to y? It's actually 0 because x and z are constant when we do partial with respect to y, so 0. Minus partial of fy with respect to z. So I need to do the partial, sorry I was blocking that. Yeah. So now I need to do the partial of y with respect to z. So this is going to be 2y squared z. Then plus y hat times partial of f of x with respect to z. So I need to do the partial of this with respect to z. So it's going to be 2x squared y squared z minus the partial of f of z with respect to x. So I need to do the partial of this with respect to x, which is going to be 2x z squared. And then plus z hat times the partial of fy with respect to x. So it's the partial of this with respect to x, which is 0. Minus the partial of f of x with respect to y, which is the partial of this with respect to y, which is going to be 2x squared y z squared. Okay? And this finalizes this. So this is a vector field which depends on x, y, z. Okay? And that's it. That is the curl of vector field f. So that is all there is to the calculation of gradient, divergence, and curl. You can see that the names are scary, but the actual concepts are very, very simple. And well, you can now go ahead and practice doing all of the problems in the workbook, in the PDF, because the rest of the chapter is just going to talk about the meaning of these operations and the properties that they have. Okay? Thank you very much. See you in the next video.